And on your right-hand side, you will find that there is a Q&A section. So if you have any questions throughout this presentation, please feel free to type in your questions there, and we will definitely address it at the end of the webinar. Okay, or if you have any statements, or if you have any points or area of focus that you are interested in, do let us know, and we will see how we can address it. So without getting on any longer, let me first introduce you to our speaker for the day. So first up, we have Mr. Michael Loffer from Kistler. So Mr. Loffer is a product manager in DEC for our business unit test and measurements. And he has a vast experience in high precision measuring instruments, electronics, and also managing high-speed network equipment. Right, he is the electrical and engineering graduate, and he also has a degree in business administration. And Michael has been with us for 13 years now, so he has a lot of experience in Kistler, and he knows very well from the sensors to the electronics that we use in Kistler to analyze our data. Our second speaker of the day is Mr. Teddy Teo. So Teddy Teo is our regional service engineer for Kistler Southeast Asia. So in future, if you need any support, he is definitely available to extend his service to you. He is an application expert in our industrial products, such as joining systems, advanced manufacturing, and also in our weigh in motion system. So he has a background of mechatronics engineering, and he has been with Kistler for at least 5 years now. So together they have a combined experience of many years. And I hope this session will be beneficial to you. Without further ado, I will pass the session on to Michael.
Thank you very much, Kevin. Yeah, thank you for this introduction. So I straight go ahead with the content of the presentation. As Kevin said in the introduction, it's about the full measuring chain with a little focus on data acquisition and visualization and analysis today. But yeah, let's have a look in the measuring chain first. So if we see or look at this picture, we see the measuring chain from sensor, cable, signal conditioning, data acquisition, visualization, and analysis. And every single component of this measuring chain is important if you want to get the results in the end. So starting from the sensor, which converts the physical signal to an electrical signal. That's so far clear, I guess. Then the cable, simple function, transmitting the signal from the sensor to the next stage, to the electronics, most of the time signal conditioning device. The purpose of this device is actually to manipulate or transform the signal into a signal which can be acquired with data acquisition in the end. So most of the times is amplification, but it may be also transformation from like a charge signal to an electrical voltage signal. Data acquisition also actually clear, analog to digital conversion nowadays. I mean, 20 years back, we had still some analog recorders, but today, of course, everything is digital. So converting the analog signal to a digital signal, but also store the signal for further analysis. And last but not least, the visualization. That's actually the goal of the full measurement. We want to have the data in order to analyze it, to draw conclusions out of it, to innovate also. And yeah, that's the main goal of such a measuring system, to get data for analysis. Two more statements for this chain, for this measuring chain. It's more common that sensors have integrated electronics, including signal conditioning, like IP sensors, but also sensors which have already digital output or possible today, let's say like this. But let's go for the normal case, or for the usual case, with an analog signal from sensor to data acquisition. Far more common actually is that we have devices which are taking care of the signal conditioning part and the data acquisition part in the same device. That's very common nowadays, but and we see that in the next couple of slides. In some cases, it might make sense to have an additional signal conditioning device for special purposes. So if you have the task to measure something, to select sensors and electronics and data acquisition and so on, to get some data, you have this task to do that. So what do you do? So you have to think about what do we really need. And so for that, we have a little checklist, and I hope this helps. By the way, if you're interested, we can hand you the presentation after the session in a PDF, so you have the checklist in an electronic form. So if you want to select this full measuring chain, let's start with the sensors and cables. What are the points to consider? First of all, I have to understand, what exactly I want to measure, what measurement. Most of the time it's clear, but there may be situations where there are different solutions possible. So it's worth to think about what results do I want, and how how can I get that? Do I need to measure force, strain, pressure, temperature, and so on? Then you have to think about how many axes. For example, for force sensors, this is a triaxial sensor, single axis, or also for acceleration. These are the questions to cover from what I want to measure. Then also very important, what signal do I expect in the end? What is my amplitude? How big is the physical unit I measure? How many newtons? How many Gs? What is the frequency range? Also very important. Is it a slow signal? Is it a fast signal? Things which are important when selecting the sensor. Then, but also mechanical issues, like how can I mount the sensor? For example, for accelerometers, do I have to glue it on the surface, or do I have the possibility to bolt it? Same or similar to force sensors. How to integrate it into my system I want to measure. Do I need a preload force? All things to consider. Furthermore, what is my environment? What's the ambient temperature? What's the humidity in my room when I do measure? Are there any fluids or gases which may influence the measurement on one hand, but also which may be harmful for the sensor? So for some situations, you maybe need special sensors which can reach a temperature range up to 700 degrees or something like that. That's all possible, but you need to know it, and you need to search for the right sensors with that. And often forgotten, the cable. It may also be very important, not only the length from the sensor to the measuring system, but also type of connectors, and very important, the sensor cable may have a big influence on the quality of data in the end. If you have a bad cable, you may face issues with noise and electromagnetic influences, ground loops. I have to consider all things like that. So cable may be an important topic. Okay, let's proceed with the electronics side. So signal conditioning and data acquisition. Also here, some things to consider. First of all, yeah, what signal do I expect from the sensor? Is it a voltage output which I get, or millivolts, like from strain gauges or so? Is it charge, like from our piezoelectric sensors? Is it a current output? So I need to know that to select the right amplification stage. Then is the sensor an active sensor or a passive sensor? So does it need a power supply like IP sensors or another external power supply like transmitters? Yeah, just things to think about how to power the sensor if required. And then linked to the signal of interest, what is my expected signal bandwidth? And from that, I can select the sampling rate, and define the anti-aliasing filter frequency. Need to think about configurable filters maybe to filter out noises which are in the frequency range, which is not interesting, stuff like that. For some application, it might be also very important to think about the signal to noise ratio. If I have, or if I want to measure very low signals, then there might be influences from external, which gives me noise. So I have to have a look into that, analyze, yeah, what is the smallest signal I can measure with the system, and yeah, select the right electronics for that. And last but not least, where I can put the devices, is it close to the measurement? This is far away. Is need or do the devices need some protection? Like if it's outside, do I need some dust-proof housing or something like that? Where I can place it? Is it an instrument on my table, like in the laboratory? Is it in industrial areas where I can use thin rail mounting, stuff like that? Yeah, so as a short summary about this list, small checklist to go through. It makes sense to think about every point here on the list. Some of the points are maybe easy to answer, some are more critical. And yeah, actually a good hint to, if you have any questions about the selection of sensors or electronics, feel free to contact Kistler to tell about what you want to measure, and we can support you with giving you assistance of selecting the right sensors and electronics. So this for the checklist. So in the next couple of slides, we will go through an application as an example. And I've selected this very nice application about a reaction wheel test. That's device. This device here on the left side. And actually, it's about satellites, so space application. So you may know, you don't have to know, but you may know that nearly every satellite has a so-called reaction wheel. That's a rotating mass inside, which is used to do the fine positioning of the satellite. So if this rotating mass is rotating slower, then the satellite goes in the one direction. If it's rotating faster, then it's going in the other direction. So that's the main purpose of this reaction wheel. And yeah, now if we assume that's a satellite which takes pictures from the Earth, maybe for weather observations, or like just for doing photographs of your country, then it's very, very important that the satellite remains really stable in space. So every little vibration which is on the satellite would harm the quality of the picture. So it's really, really crucial here that this rotating part here is not influencing the satellite with these micro vibrations. We see an example diagram here on the right side, a waterfall diagram, where on this axis we see, of course, the amplitude of the vibration, and on this side the speed, and here the frequency parts. So we see clearly the main signal. Depending on the speed, we have higher vibrations on the satellite, and here we see some how it's called, some harmonics. And the goal actually here is really to, first of all, measure all these vibrations, and second, then to find ways to reduce these vibrations in order to have a better quality of the satellite pictures in the end. So that's a short introduction about the application, and we will go now through step by step, selecting the right components for that. So first of all, let's start with the sensor. Here I have again the checklist for the sensor selection with already the results or the conclusions. So for this application, we want to measure forces and moments. For that, you could use like strain gauge sensors or our piezoelectric dynamometers, like here in the example. That's exactly the point here. What's my expected signal? In this case, they're really small vibrations. So we know from experience that the measured forces are in the range of 0.1 millinewtons. That's not a typo. That's really millinewtons up to 1 Newton. So really small signals. But this whole installation with the rotating wheel has an own mass. So if we would place such a mass on a kind of a standard strain gauge sensor, we would measure mainly this mass, but not the vibration. So here our Kistler piezoelectric technology has really advantages that we can place the mass here and to do like a tear. And then we can really measure all the small, really tiny forces. So it's really an important step here. So in this case, how can I mount the sensor where it is placed? In this case, it's a laboratory measurement actually. So I need a little bit of space to place the sensor, to place the satellite part. Important here also is that vibration isolated table has been is used, because if you place that just in the laboratory and you walk by, then you would influence the measurement in a way that you can't use it. So in this case, you need really to take care about the installation. Ambient conditions are not critical, as I said. Laboratory application, standard temperatures, standard humidity, yeah, just normal air. It's no issue. Cable also no big issue. We need to place the equipment maybe 5 meters apart, this sensor. Important here, we will see that just on the next slide, is that we need a high insulation cable, and of course low noise, because we have really small signals to measure. So yeah, let's jump to the cable. Yeah, I mentioned here for piezoelectric sensors, you maybe know, if you work with piezoelectric sensors, that we need a high insulation cable, that just to prevent the signal from drift. It's just like that. It's no big deal. But also maybe important is that if you use such a cable, if you move the cables, they can introduce noise. So it's on one side important to keep the cable kind of not moving, or to use low noise cables. That's may be important depending on the application. And also here, like not only with charge signals, also with piezoelectric sensors, but also with other signals, voltage signals, cable length may have an importance. Cable capacity may reduce the frequency range on one hand, and may also increase the noise level. So as I said in the introduction, the cable may be important, so take care about that. General statement here for charge measurement is up to 30-meter cable length with frequencies below 50 kilohertz and charge values above 500 picocoulombs. That's no big deal, but just to keep in mind, synchronous about it and clarify if this is the case. Okay, so let's move on to the next stage. And again, the reminder, if you have already questions, feel free to type in already. We will answer them all together in the end of the presentation. So next component in this measuring chain is the signal conditioning part. And I mentioned that nowadays most of the electronics include signal conditioning and data acquisition. But exactly for this example, it makes sense to use a dedicated signal conditioning device, and just explain why. Again, here with this very, very small signal we have, this 0.1 millinewtons up to 1 Newton, we expect a charge range from the sensor from, I have to read the numbers, 0.0004 picocoulomb up to 10 picocoulomb. That's very, very slow amount of charge. That's kind of, yeah, that's some electrons, not many more, let's say it like this. It's, yeah. The advantage of a charge sensor is you don't need a power supply. It's kind of an active sensor. If you press the sensor, it generates this charge automatically. I will explain it on the next slide. The expected signal bandwidth here is 1 kilohertz. So the rotating speed is not that fast. It's so maybe 10, 100 rotations per minute. So not that high signal bandwidth expected. So 1 kilohertz signal bandwidth, as a rule of thumb, you would have to choose the sampling rate 5 to 10 times higher. So we go with 10 kilosamples in this application. And linked to this very, very small charge range, yes, signal to noise ratio is very critical here. So that's why we've chosen this Kistler charge amplifier, which is really the best in class amplifier. And I don't say that only because I work for Kistler. That's really the case. That's the best charge amplifier which you can get on the market. It's also not cheap, I have to confess, but it's really the best thing you can get. So for this application, this is really critical. So this is the way to go. Therefore, also an external device, really a dedicated charge amplifier and not included. Again, if the application is not that critical, an integrated charge amplifier is also okay. Last point, not that critical. It should be so more or less close to the measurement object, but as I said, we are in the laboratory. It's all static. That's no big deal. Up to 5 meters, that's no big issue. So then I digress just for one slide. For those of you are not really familiar with the charge technology, just one slide. So we have here the principle of a charge sensor and a charge amplifier. So the charge sensor consists of a crystal, or how it's called, maybe you can help me with the English name. Yeah, a crystal. It's a piezo element, which generates a very small charge if you apply a force or pressure or something like that on it. So with every force, it generates a negative charge value. So here in this sine wave simplified. So force, and then we have a charge value. And charge is kind of a special electrical signal. You can't measure that directly. So therefore, you need this charge amplifier. The principle is actually quite simple. That's an amplifier stage which is built as an integrating amplifier, actually an inverting integrator. So the charge is flowing from the this sensor into this capacitor. That's a so-called range capacitor, and this generates the output voltage in the end. And by coincidence, it's an inverting integrator, so the negative charge signal we get out of a positive force will result in a positive voltage in the end. That's the good thing about that. Then just two details. One of them is the reset switch. That's the one used to reset the whole electronics before the measurement. So you start really with 0. That's especially for this application, it's very important. So that's used in so-called quasi-static charge amplifiers. For pure dynamic measurements, there are also dynamic charge amplifiers available. They're a little simpler to build. They have an integrated time constant resistor. That's how it is called. So this actually discharges this range capacitors after a certain amount of time. So if you measure fast signals, you will see that at the output, but after a while it goes to 0 automatically. That's the purpose of this time constant resistor, which is used in pure dynamic measurements. Okay, so let's go to the next slide. I've said in this application, noise is very critical. I don't want to go into detail here about noise because it could be really a huge topic. Just a short introduction. If you compare the electronics or also sensors and so on with noise values, it's helpful to remember these 3 type of noise specifications. So the first one is actually very simple to understand. So if you measure the noise over a certain time, we just look at the signal and read out the peak value. That's okay. That's easy to measure. The difficulty here is the longer you would measure, there would be somewhere a real big spike, and if you measure just for 10 seconds, 30 seconds and define the noise specification, then you don't get everything which can occur. So maybe here it's a big spike, which would really increase the peak-to-peak value. So it's, as I said, easy to understand, but not very good to describe noise specification. Second possibility to specify noise, and that's my favorite one actually, it's the so-called RMS, root mean square. So the noise signal is kind of recorded, and then the square root of all the values is generated, which creates kind of this yes, mean value, this root mean square value. Last option to specify noise, and that's really for the experts, is the so-called power spectral density. So here the noise is not specified or not measured. It is measured over time in the end, but it's specified over the frequency range. So in the spec sheet, you would see noise values for different frequency ranges. And that's, for some applications, might really helpful to select the right device I want. But as I said, it's not that easy to understand. You would have several values, which as a specification, which gives this graph here in the end. Just a little hint or a little trick. If you want to compare the noise values, and if you compare it mainly with the RMS value, there's a rule of thumb. If you have a peak value, you can divide it by roughly 6.6, and then you have approximately the RMS value. That's really a rule of thumb, which is true for real white noise, but in real world you don't have 100% white noise, so it's really an approximation. If you have values from this power spectral density, then you would need to take the square root of the integration of all these noise values. Yeah, you can do that. You can calculate that it's possible, but it's also not easy to understand this whole specification here, because the unit of such a noise value is microvolt per square root hertz. I can't imagine that, so that's why my preferred specification is RMS. Okay, so I go ahead. Next topic, data acquisition. So here actually it's that complicated in the end, just a short introduction. What does data acquisition? As I said in the beginning, it takes the analog value and transforms it into a digital value. And you may have seen in datasheets, or you know it, that there are different types of ADC or AD converters, like analog to digital converters, with different so-called bit width. So we see here the example. If we would have an AD converter with just 3 bits, we would get only very few numbers out of the analog signal. So the analog signal is divided in the vertical axis in these bits, or in the steps, which is given by the bit number, like 2 by the power of 3 in this case, like 8 values. Compared to that, to the 3-bit resolution, we have here in red the 14-bit resolution. And what you see here actually is you don't see any steps anymore. That's fine. And actually, we can say state-of-the-art data acquisition systems have already 24 bits. In the end, with the noise which is in the whole system, the effective number of bits is maybe 18 or slightly above. So if you have 24 bits, that's far more than enough. The other or the second important characteristic of a AD conversion is the sampling rate. So that's actually the horizontal resolution sampling rate. You probably know how many samples, how many values per time unit per second I do get from the ADC. That's most of the time it's configurable in the data acquisition system. Here the thing is to consider more is always better on one hand, so you get a better resolution. Also to fulfill the Nyquist-Shannon theorem, which says that you need to acquire or to have a sampling rate which is at least twice as the expected signal bandwidth. So from this perspective, higher is always better. But you have also to consider, especially for longer measurements, the more samples you take, the more data it generates. So if it's just a couple of seconds of measurements, there's not an issue. If the measurement is minutes or hours, it may generate megabytes or even gigabytes of data, depending on which exact sample rate you use, and on how many channels in the end. It's really a multiplication of channels and sampling rate. Just a little hint here, we prefer actually a binary format to store the data. Quite common is also the CSV format, like the comma-separated values, which can be used with Excel in the end. It's okay, but the binary data format is much more space efficient, so that's why we prefer that. Okay, so I mentioned the Nyquist-Shannon theorem. So from the theory, we know that the sampling rate must be at least twice as the expected analog bandwidth, where we apply the anti-aliasing filter. That's a different topic, would be also worth a special webinar. So at least twice in practice, actually, because the anti-aliasing filters are not ideal, we recommend to have a sampling rate which is about 5 to 10 times higher than the expected signal bandwidth. And one kind of personal statement here, I always try to really distinguish between the analog bandwidth, which is expressed in hertz, that's only hertz, and the sampling rate, which is expressed in samples per second. It's not wrong to express it in hertz, that's not wrong, but I like to really distinguish, and I always talk about hertz of analog bandwidth and samples per second if it's about sampling frequency. This helps to use different units for these different values, because it's really not the same. Okay. So far to some little theory. So I move on with the selection of the data acquisition system, and here it's now the point to introduce our KiDAQ data acquisition system. We have this nice little infograph about our, we call it ecosystem around KiDAQ. So on this side, we see our KiDAQ data acquisition system, which is available in different housing types. We have 20 different modules to measure a lot of things. I'll have another slide about that. With that, we are able to measure Kistler sensors, of course, charge sensors, but also other Kistler technologies, and also third-party sensors like generic voltage inputs, current inputs, temperatures, digital levels, and so on. So a complete or a family of products with modules. And the nice thing about this system actually is that we can extend it with other Kistler devices, like our lab amps, which are special laboratory amplifiers for charge signals, but also for voltage signals. They also can be integrated into the same system, which is then controlled by our KeyStudio Lab software. On one hand, our KeyStudio Lab to configure the devices and to acquire the data, and our very powerful jBEAM analysis software. We will see that just in a couple of minutes. One little detail here with this little green thing here, that's our KeyConnect technology. That's actually the thing which makes it possible to combine different measurement devices into one setup. That's our own technology. Actually, it's simple. It's based on TCP/IP protocol, like standard internet protocol, so it can be used in a local setup, just from laptop to the measurement device, but also in distributed setups. Very important, it includes the so-called PTP time synchronization. PTP stands for Precision Time Protocol. It's a industrial standard, or an IEEE standard to be exact, IEEE 1588. So with that, it's possible to synchronize times between different devices in the sub microseconds area, which is really very good and very important also if you measure with different devices, that all the signals are aligned on the timeline. With KeyConnect, we can also provide gateways to integrate more devices, also from third parties. This would be possible. In the end, we get or we have a system which can be handled by one software, our KeyStudio Lab software, and everything, all data is in one format and ready to analyze in the end. Yeah, I mentioned this wide variety of modules we have. Here again, the KiDAQ system with the different housing option, the nice portable one you can just carry around, a rack option for standard 19-inch racks, thin rail for industrial applications. And with that, we have, as I said, 20 different modules where we can measure voltage, current, resistance, temperature with PT, platinum temperature sensors, but also thermocouples, strain gauge sensors, inductive bridges, piezoelectric sensors, also IP sensors, and also digital signals, frequency, and so on. And in addition to that, our special laboratory amplifiers for charge, 2 different types, purely quasi-static device, which can measure quasi-static and dynamic, actually. The name is a little bit confusing. And the little brother, the dynamic device for pure dynamic measurements. Yeah, just 1 word, 2 words about the software, the KeyStudio Lab software. We built it to have an easy configuration with that, so it's really easy to handle that. You just go through from left to right, and then you're done with the whole setup. That's really easy, and you can do live graphs, some simple analysis, and you can define triggers when to record the measurement, and so on. So I move on to the last part from the kind of theory or the introduction, visualization and analysis. That's actually this thing which is the important thing in the end. That's the goal of the whole measurement, to have data to analyze, yeah, to innovate in the end, to draw conclusions and so on. For the visualization and analysis, we provide our jBEAM software. It's really a powerful tool, and we will see a live demo just in a couple of minutes. A really powerful tool with interactive analysis, automated reports. And I just want to explain this graph here on this slide. Where is this software positioned in the market? And we see many customers who are using Excel, for example, or another how it's called, yeah, you know what I mean, another tool like that. Yeah, spreadsheet tool. Yeah, spreadsheet. I missed the word spreadsheet. So spreadsheet tools. Yes, you can use that to analyze measurement data, but it's really not intended for that. Excel or the spreadsheet tools are intended for business data, financial data, do financial business cases, do like controlling and stuff like that. It's really not for measurement data. That's not the right tool. On the other hand, we have very special tools like math tools like MATLAB, Octave, or measurement tools, LabVIEW. It's widely used in the world, and yes, they have their advantage. I have to confess that. But the general statement here is actually that it is not intended to have a really quick way to analyze data. You need to do a lot of programming. You need really to understand how it works, and you need time to program the graphs you want, and so on. So as I said, it has use cases, or it has use cases for sure. But we really recommend our jBEAM, and I always say actually jBEAM is a tool from engineers for engineers. And with a really short introduction to understand the working principle, then it's really easy to work with, to use calculations, to add graphs, to do analysis in the graphs. Yeah, maybe a short comparison from jBEAM to like MATLAB. A couple of features which are important from my point of view. First of all, import possibilities. So with jBEAM, we support over 100 data formats. For example, in comparison to MATLAB, which supports only standard data formats. Okay, you could do other data formats, but you would need external scripts for that. Then, important from my point of view, quick measurement data analysis. Yes, with jBEAM you can do that. You just drag and drop the signals into the graph area, and then you see it. You can just add analysis cursors really quick with the analysis. In opposite to MATLAB, okay, a pro user is also quick, but then you're really a pro already and you do the programming quick. But if you don't use it on a daily basis, then you need always time to learn the syntax and so on. Same for using formulas. With jBEAM, you just select and click the values you want to calculate, and you create your simple formulas. Also here with MATLAB, only with programming possible. But I have to confess, a really extensive function set. Yeah. Interactive analysis, that's very nice from jBEAM. So you could define your graphs and you could define input fields on the analysis part, like text fields where you want to enter a filter value, or you can move around a cursor, and then all the depending graphs, they adapt automatically. Also here, programming is required with MATLAB. On the other hand, if you have really complex algorithms, yes, this is now the main purpose of such tools. You can do that. That's really the intention to do that with such a tool. jBEAM is not built to do quickly such big algorithms, but the nice thing is you could integrate MATLAB algorithms with a wrapper, or you could also write Java classes. That would be possible. And last but not least, very important from my point of view, if you want to create a report with jBEAM, it's really easy. You define in the graph area how the report should look like. You just click on export as a PDF or export as a PowerPoint, and then you get the full report. It can be done also automated, like on every new imported measurement, it creates a report automatically. It's really helpful with recurring measurements. Also here, it's doable with MATLAB or Octave, but you need really a lot of programming for that. Okay, that was the main part from my side. So I'd like to hand over now to Teddy, which will show you a live demonstration of our jBEAM analysis tool. Yeah.
So thank you, Michael. Good afternoon, ladies and gentlemen. My name is Teddy, and I would like to share about the jBEAM software on vibration analysis. Okay, so if you can see my screen here, this is the jBEAM software. And I have here a report template that I created to be used for vibration analysis. So first, on the first graph here, I have the raw acceleration signal from an accelerometer on this graph. So this measurement signal is imported from the KiDAQ data acquisition unit in the format of an MDF file. So as you can see here, it is only one out of the over 100 data formats available to be imported into jBEAM. So back to the graph, looking at the acceleration signal, I think that the signal is quite noisy, and I would like to apply a filter to filter out the noise. But what threshold should I set for my low pass filter? And here is where my second graph, the FFT, comes into play. So using jBEAM, I can easily create an FFT graph of my acceleration signal. And now with the FFT, I can identify where are the noise signals on the frequency domain and try to filter it. And over here on my third graph is the filtered signal. So I set an interactive input for my low pass filter. That means that the frequency for my low pass filter is set by this cursor here. So as I slowly move it to the left, we can see in real time that I'm filtering out more of the noise and my signal gets smoother. So I'll stop about here, and now I have my filtered acceleration signal without the noise. And I'm ready for more analysis. So next, I would like to integrate the acceleration signal here to get a velocity signal. Doing this on jBEAM is just as simple as finding the integration tool, typing a name for my result, selecting the input data, selecting integration, and click OK. And just like that, I can drag and drop, and there it is. I have my velocity signal. And it is the same graph as what I have created here earlier with the same steps. So let me remove this. And now with the velocity graph, I can repeat the integration steps to get a displacement graph as well. And finally, I set up a few displays here to show some key values: the peak acceleration, the peak velocity, the peak displacement, my dominant frequency, and also my low pass filter frequency. And after getting these data that I want, I can export all this into a PDF report. Go in here and export a PDF document. So export. And now we have it. This is the PDF document. So on this document, it looks exactly like...
We don't see the PDF document because you share only jBEAM.
Sorry about that. Okay. So you see the document? Okay.
Yes, now it's visible. Yeah.
This is my PDF document, and it looks exactly like what I have set up on jBEAM. So I have the original signal, my FFT, my filtered signal, the velocity, displacement, and my key values, together with a report generation, date, and time at the bottom. So back to jBEAM, I have made multiple acceleration measurements, and I can easily and quickly do the same analysis I've done on ladder measurement data by importing another file. And now with a new acceleration signal, all my graphs here are updated automatically, and I can just quickly generate a report like before to get a report on my new data. And all this is done with just about half an hour on jBEAM. And this concludes my jBEAM demo. Thank you for your attention. So back to you, Michael.
So thank you, Teddy. And just an additional statement here. With this data import and report generation, both steps can also be automated. So if you have a lot of recurring measurements, you can set up jBEAM in a way that it imports new data which is in the directory automatically and generates also automatic report out of it. That's a very nice feature which is included in the jBEAM professional version. Good. We're nearly at the end of our session. Just a couple more slides. On the first one is just to underline the versatility of jBEAM. Yeah, with a very different application. So some of our customers use jBEAM also for engine-related tasks like combustion analysis and so on. So we see here the use cases where it is used. Yeah, this takes a little more to set up all the graphs, of course, but it's possible with jBEAM. Just to show that, yeah, it's really versatile and you can use it for very different things. Of course, for engine applications, we have our Kistler KiDAQ. Maybe you know that if you're working in this part. So we don't want to compete with that. So the KiDAQ is really also a nice tool for engine applications. But if you just do something as a one-time thing, you can use also jBEAM. If more flexibility to use your own formulas, you can do more own calculations and auto views. In opposite to KiDAQ, which has predefined setups, which makes it easier to do all the standard measurements. Let's say it like this. Okay, so yeah, as a summary, we go a step back. If you think about again the application we introduced in the beginning with the microvibration with this reaction wheel, as a summary of the whole selection of the measuring chain. Yeah, we had this reaction wheel which requires to measure very low forces with the sensor. It's a quartz dynamometer. We talked about the cable, which might be very important regarding noise, electromagnetic influences, and so on. Signal conditioning, which is important generally, yes, and also or especially in this application with this really high or with this high requirement regarding signal to noise ratio. We talked shortly about data acquisition, our KiDAQ data acquisition system, which can handle hundreds of channels depending on the sampling rate and can go up to 100 kilo samples. And we've just seen the visualization and analysis with jBEAM. And Kevin did or stated this sentence already in the introduction, and I think it's really an important statement. Also, a measuring chain is only a chain, and therefore it's only as strong as its weakest link. So for the last words, I hand over to Kevin again. Thank you.
Okay, thank you very much, Michael and Teddy, for that wonderful presentation. So I guess this concludes our webinar. I just want to say that in the past, Kistler has been able to support you with the sensors and with the signal conditioners. Unfortunately, we did not have the data acquisition and the software part, but in the last few years, we have worked very hard. I think Michael is heavily involved in this project as well. And we are glad to now inform you that we can support you in the whole measuring chain. So whether it is from a sensor to the data acquisition to the analysis software, you have seen in this 1 hour presentation. Unfortunately, we cannot cover all the features that is available in the jBEAM and in the KiDAQ. But we have provided here a short summary for you that you can consider if you are looking for a new data acquisition system. So the main benefit that we offer, first of all, is that the KiDAQ unit is modular. And what I mean by this is that if you see we have individual measuring cards with the ability to connect to different types of sensors. So if you are doing a measurement with pressure sensors, then you only need to get a card that has a pressure input. Or if you are more interested with vibrations, then you purchase the KiDAQ with the vibration card. And this way it's very cost effective. You only get what you need, and you don't need to buy 16 channels or 32 channels, which is quite common in the market. And it offers you with great flexibility. I would say the second benefit that we offer is we have a wide selection of inputs. So you can see, I think Michael has mentioned we have over 100, 20 options, right? From voltage to current to temperature. Yeah.
20 different inputs here. 100 would be the number for the data format for jBEAM. Yeah.
100 maybe in a few more years. Yes. So yes, if you have a need, do check with your local sales rep, and we can recommend the appropriate modules for you. Another benefit that was highlighted was the precise time protocol, the PTP. So this is really important because when you're doing measurements across different devices, across different channels, and across different sensors, you want to make sure that the timing of all of this is captured correctly, because the last thing you want is that your timing is off because of some delay within the electronics, and then it gives you maybe a different results, or you analyze the test in a different way because of it. So this is one of the guarantees that we give to our customers who purchase our system. Of course, not forgetting also we have a very high sampling rate, so up to 100,000 samples per second. And I think this one is sufficient for most of the tests that we do in this region. And not to forget a powerful analysis software. So this one, Michael has spoke a little bit about it. It is in a nice balance in between an Excel sheet and maybe a more complex or more bigger version like the MATLAB. So one thing I can share is that we had a customer who was doing some research. They are from the R&D department, and he was very good with MATLAB. But the moment he left the company, immediately nobody could continue his research because nobody knew how to work or operate MATLAB. So I hope that the jBEAM is a very nice balance between a programming tool and also ready-made software where you can actually pull up the functions according to your research. So if you have any questions, feel free to speak to your local sales rep, and we are always happy to support you in your projects. So I think we are already a little bit ahead of time or behind time. So I get on to the questions. We have quite a few now. First, we have a question from Rifalino. Sorry if I pronounce your name wrongly, but yes, so Rifalino mentioned she's interested to get the video recording. Yes, definitely, we will share with you the link of the video recording, and I believe we can also share with you the presentation file.
Yes, yeah.
Yep. Okay, the next question from Melvin Chan. He would like to know about jBEAM. Does it work for all Kistler products? So
good question. I'm not sure if it works for all, but I mentioned that we can import 100 different data formats. I would guess it works for most. I would have to check in detail if you have something specific in mind. Yeah.
Okay, but definitely for the KiDAQ it would work, and
yes,
if they have
for KiDAQ,
sensors,
yeah,
yeah,
and also a lot of other Kistler Kistler devices. Yeah, because we use MDF often, but also other formats which are integrated into jBEAM. But I would lie if I would say if it works for really every, but for most it will work. But yeah, again, just tell us which one, and then we can clarify. Yeah.
yes. So Melvin, just contact your local sales rep, and yeah, he will get in touch with us, and we can give you the answer. So okay, I have some more questions. Let me see. From Safian. So he's asking, what is the difference between MATLAB and Kistler jBEAM? I think Teddy has shown a little bit about how the jBEAM function, but if you want to know more, what I would suggest is contact your local sales rep, and we can give you maybe a live demo, because I believe some of the countries we have demo systems, or we can even do it online, so you can understand better what are the features that or functions that you can do with it. I hope that
and
yep.
we can also provide trial versions. That would be also
yes.
possible. Yes. Yeah.
Okay, that's nice. Yep. So, Safian, if you are interested, do let us know, and we can provide you this trial version. Okay, maybe I have time for one more question. This is from Rona Was. So Rona Was is asking, how is the licensing of Kistler software? Do I need to renew the license every year?
No, that's not the case. It's a normal software buy. You buy the software and then you can use it as long as you want. For the first year, we include also the updates. But if you want to have updates after a year, then you would have to pay a small maintenance fee. Yeah. But it's generally it's a buy software, not a renting software. Yeah.
Okay. Thank you, Michael. So actually, I think that's all the questions that we have from the group. Yep. So I think we can close the session now, but if you have any other questions, do feel free to drop us an email, and yeah, we can get back to you with the answers. So thank you once again for your time, and hope to see you guys soon. So with this, I close the session. Thank you very much.
Thank you. Goodbye.
All right.
Thank you.
Bye.
Bye.